So today I'll be talking about selection problems in the presence of implicit bias, and thanks, Bobby, for that great introduction. So I'm going to start off with a little bit of background on what implicit bias is and how it's been studied, and then we'll move into some technical questions surrounding it. So it's also known as unconscious prejudice, and it's been pretty well established in the literature. Some of you may have seen this famous study by Bertrand and Mullainathan, where they took identical sets of resumes and just changed the name at the top. And it turned out that when you put a traditionally Caucasian name at the top, they would get something like a 9.5% callback rate. And it turned into something more like 6.5% when there was an African-American name, purely based on the resume when they were identical. In a more kind of closer to our fields, Wenners and Wold did this study. It appeared in Nature in '97. And it was about academic hiring in Sweden. And they included this plot. And let me explain what this means. So the part of the evaluation that went into whether they should hire these postdocs or not was this subjective evaluation that there was a committee of 5 members. Each one would rate each applicant between 1 and 4 for various attributes. One of these attributes was competence. And they found that the competence scores assigned to women were systematically lower than what they were for men. So they actually went and tried to figure out why this was. So the y-axis here is the competence score that they were assigned. My x-axis here is its total impact. And this was supposed to basically, they were trying to make some objective measure of scientific merit. And so what they did was just like a weighted sum of the number of publications weighted by the kind of prestige of the journal in which that publication appeared. And what they showed was that there was actually no scientific reason that explained the systematic differences in competence scores. And so this to them was evidence of bias. Actually, another interesting finding they had was one other predictor of getting a high competence score, independent of this total impact, was whether or not you knew somebody on the committee, which is why the title of this article is actually Sexism and Nepotism in Peer Review. Okay, so what do people want to do about bias? What are some mechanisms that you can actually use to counter them? As Bobby mentioned, in 2002, the NFL instituted this policy, noticing that the fraction of head coaches who are African American was significantly lower than the fraction of players who are African American. And so the policy was as follows. All you have to do is interview some minority candidate whenever you're hiring a new head coach. Okay? Seems simple enough, and it turns out that this has grown beyond the NFL recently. Eric Holder recommended that Uber adopt this after numerous scandals that they had, and other tech firms have been trying to use this as well. And the claim in this subtitle is the Rooney Rule worked in the NFL, can it work in the tech industry? And so what they're claiming is that the Rooney Rule actually improved diversity. Here's some evidence that hopes to show this. What they're comparing is the orange line here is NFL head coaches who are subject to the Rooney Rule starting in the 2002-2003 season. The black line here is NFL coordinators and NCAA coaches who were, in fact, not subject to the Rooney Rule. And so you see this jump right around 2003, suggestive that the Rooney Rule was actually having a positive impact on diversity here. Okay, so there's some evidence that shows that it actually does help with diversity, and you would expect that this would be the case, right? What I'm going to be focusing on instead, actually, is the effect that Rooney Rule has on the quality of the interviewed candidates. Okay, so you would in this world where you have implicit bias, which is some departure from the optimal action of hiring or interviewing the best people, the question is, can the Rooney Rule actually reverse this and get you to interview better candidates? Okay, so in order to analyze this, I'm going to need to throw a model at you. And so it's going to be as follows. The world is divided into X candidates and Y candidates. My X candidates are going to belong to some minority, and therefore the Rooney Rule will be designed to protect them. And I'm going to say that all the qualities of these people are drawn from this common prior, some heavy-tailed power law distribution. You can, of course, argue that this common prior assumption may not be true in practice, but I would say that this is probably the first thing that you should study in a model of this sort. I'm going to assume that I have n Y candidates and an alpha fraction of X candidates. So alpha n X candidates, n Y candidates. Okay? And then now I need some mechanism for this bias to operate. And so it's going to be as follows. The simplest thing you might want to do is just say the qualities of the X candidates are just divided down by some constant beta. Okay, but importantly, I can't actually observe these qualities because life would be way too easy if we could. But what we know people can do in practice is rank. We know people can choose the top K. Okay, so the way that our model is going to work is that you have to interview k people. Naturally, you would just pick the top k in this ranking. Okay? And because there's some bias against these x candidates, it's not going to be a true ranking. There's going to be some skew in it. And so what's the effect of the Rooney rule here? Well, if at least one of my top k candidates comes from is an x candidate, then the Rooney rule does absolutely nothing. It has no effect on who you interview. However, if all of my top k candidates are y candidates, it simply says replace the worst of those with your best x candidate. So in this case where I need to hire 3 people, the top 3 happen to be y candidates, so I'm going to replace number 3 here with the best x candidate. Okay, and this is in the hope that because the bias has kind of downweighted this x candidate, it might actually be closer to the true ranking if I were to bring them back up. Okay, and so in our model, the main question is going to be, for which of these parameter values does the Rooney rule actually improve your expected quality, and how does it kind of vary with these parameters? Okay, and the intuition I'll give is there's 2 possibilities, right? One possibility is that the bias has caused you to choose a weaker candidate, and actually the Rooney rule is correcting for this. The other view you might have is that, let's say we have very small amount of bias or very few minority candidates. It might be the case that the Rooney rule is actually reversing a decision that was correct, in fact. Okay, so the question, how can we answer this question, right? So it turns out we need to be working with something that looks like this, okay? And let me get into the notation a little bit. So when I use these parenthetical subscripts, they're going to be order statistics. So x sub alpha n is going to be the best x candidate. Y sub n minus k plus 1 is going to be the kth best y candidate. Okay, so what this is saying is, conditioned on the fact that none of my top k candidates in my ranking was an x candidate, what is the effect that the Rooney rule has? Because I'm swapping in this best candidate for the kth best y candidate. Right? So this is exactly what the thing that I was hoping to solve for. Okay? And I'm going to kind of reformulate this in a way that makes it a little easier for me to work with, which is just going to be the ratio in their expected qualities. Okay? Whenever this is bigger than 1, the better thing to do for my utility was actually to interview this x candidate as opposed to the kth best y candidate. Okay? So there's some challenges we're going to run into. One of which is that less is known about order statistics than you might think. And another one is that conditional expectations are surprisingly complex, and we'll get into some fun puzzles surrounding this, actually. As a nice kind of warm-up fun fact, just a quick question, what is the expected maximum of n samples from a power law? So it turns out that this actually is pretty nice to reason about, and you get something that looks like n to some fractional power. So if my delta is like 1, and I'm looking at 100 candidates, the expected max is something like 10. Okay, so let's get into the main result here. The main result is you can actually get a pretty accurate characterization of this ratio of quality that we were talking about. And surprisingly, it doesn't even depend on n. So essentially, we're in a world where it doesn't actually matter how many applicants you have. Whether or not this Rooney rule is doing good things for your utility only depends on these other parameters. For kind of just to show that it can be somewhat concisely written down, I'm going to throw a formula up here. This is, if you're hiring 2 candidates, this is the decision rule you should use, whether this kind of ugly mess is bigger or smaller than 1. The point isn't to try to parse this, it's just to show that it does exist. It gets more complicated for larger values of k, but for 2 candidates that we're hiring, this is kind of what we have. And this leads you to a conclusion that looks like there's some critical level of bias such that if your bias is above this critical level, the Rooney rule improves your expected utility, otherwise it doesn't. And you might tell me, this is obvious. Obviously, it should be monotone in this parameter beta here. And to that, I'll say, wait until 1 or 2 slides from now, and we'll get into why it's not so obvious. Okay? And so to give some intuition about what this function actually looks like, because it's just kind of a huge mess, this is it. Okay? So you'll notice some surprising features of this landscape, one of which is this kind of valley that persists here. And it kind of seems to cut off right around, so let me give you my axes here. This is alpha, delta, and beta. right around alpha equals 0.3, it seems like this valley no longer exists, and it turns out to be monotone where previously it wasn't. There are actually good reasons for this. It turns out that this cutoff point right here is 1 over e. And I'll actually get into why that is. And I'm actually going to give you the answer to the puzzle that Bobby posed at the very beginning. And to set it up, I'm going to phrase it in a slightly different way. One way of looking at this is what part of this alpha delta plane is even covered by this surface. Because if you remember, right around alpha equals 0.3, it seemed like this thing tended up to infinity. And qualitatively, the way of looking at this is, as I get to a world of infinite bias, when is the Rooney rule improving my utility? And this world of infinite bias is what Bobby was talking about when maybe another way I could say it is, let's say I'm admitting grad students and I get applicants from, let's say, China, which is something I'm pretty good at evaluating, and a couple from Afghanistan, which I'm not. Maybe I know how to rank them all relative to each other, but I don't know how to interleave these rankings of grad students from different countries. And so let's say my natural tendency is to say, well, I know a lot about these Chinese students. I can actually rank them pretty well, and I know that they're going to be pretty good. My estimates of the Afghani students are not very good, so my normal way of ranking them would just to be put them all at the bottom. So with the Rooney rule would, or without the Rooney rule, I would end up taking the top 2 students from China. But if the Rooney rule were instead to force me to say, I'll take 1 from China and 1 from Afghanistan, what should I do? Which is actually going to give me more utility? And so it turns out that there's actually a surprisingly simple resolution to this. So I'm going to say, I'm going to denote by z star the expected maximum of n candidates. I'm not going to say exactly what it is because it's a little bit of a pain. But I can define everything relative to that. So if my choice is between the second best y candidate, my second best student from China, I can tell you that the expectation is delta over 1 plus delta of the best one. Okay, it's just a nice constant factor below. What about my best x candidate? Well, it's a different constant factor below. It's alpha to the 1 over 1 plus delta. And so if I put these together, when is my best x candidate better than my second y candidate? Whenever this condition holds. And for those of you who are very quick, you'll notice that that expression on the right-hand side tends to 1 over e as delta goes to infinity, which is what actually produces that ridge up at the top, anywhere below alpha equals 1 over e. Okay? And the other surprising consequence of this, well, first of all, so this is what this plot looks like. And what we get from this is that for every positive alpha, there is small enough delta such that expected utility increases if we reserve 1 slot. So it's saying if the 1% of your applicants come from Afghanistan, you'd be better off, if you believe that that this distribution is heavy-tailed enough, you'd be better off always reserving 1 slot than never taking them at all. Okay? Now let's move on to some unexpected behavior from conditional expectations. So this is another thing that we found kind of surprising and puzzling. So one of the basic objects we work with is for some, let's say I have 2 random variables a and b and some constant c. I want the expectation of a conditioned on the fact that it is a constant factor bigger than b. Okay? And so I want you to consider this as a function of c. Do you believe that this should be monotone in c? Turns out no, even if a and b are IID. So let's say a and b are both uniform on 1, 5, 9, 13. You get a grid that kind of looks like this. This is the joint density. And consider 2 cases. So, okay, first of all, intuitively, it should be the case that as c increases, you're saying a has to be bigger and bigger, so its conditional expectation should be getting bigger. For most distributions, this seems to be true. But if you look at this example I have here, let's say I condition on the fact that a is bigger than 2 times b. It turns out that the conditional expectation, well, this restricts us to these bottom 4 points here. And over those bottom 4 points, the conditional expectation is 10. Right? But conditioning on being 3 times bigger than b instead, I get something like the bottom 3 points, and the conditional expectation over those points is 9. So it gets this surprising non-monotonicity in C, and that's actually not something we were able to resolve. So if anyone wants a fun combinatorial problem or probability problem, for what distributions is this object actually monotone? We don't actually know.
Do you have counterexamples for distributions with no atoms?
No, we don't. Or actually, I mean, yes, if you can just like very gently smooth these things out, so this counterexample will still hold. I suspect that for distributions with only one peak, this might be actually, you might be able to get this to be monotone. But I don't know. Okay, and so the last thing, or one of the last things I'm going to show you actually is a kind of interesting step from the proof that gives us some intuition for what bias actually does to a population. So there's an ugly integral here, but this is essentially as follows. This is something like the expectation of y conditioned on the fact that it's beta times, or it's beta times y is bigger than x. Okay, so I have my conditional expectation here. This looks almost like this ugly, other ugly integral, which you've noticed that this kind of term right here, this term has kind of stayed the same, and I've squeezed these two terms together to get this. Okay, don't worry too much about it, but the kind of interesting insight from this is exactly the PDF of an order statistic from a power law drawn with more samples. So what this is really saying is that the way that bias operates is it essentially simulates as if one population were drawn from more samples than they actually were. Or alternatively, that the minority were drawn from even fewer samples than they actually were. Okay? It's not exactly analogous. There are some key differences between them, but we do see this kind of, especially in our solutions, we see this equivalence almost between decreasing the size of the minority and increasing the size of the bias. Okay, so that's kind of an interesting qualitative insight about what bias is actually doing. And the final little piece I want to show you is that techniques like this can be actually used to do something like estimate from historical data how biased you actually are. So let's say I'm in a setting where every year I've hired one person. I'm not using the Rooney rule or anything here. This is just, I'm just hiring whoever I want to. So what we can do is use our techniques to show exactly what the probability that you hire an X candidate is, given that you have some certain level of bias. Okay? And kind of keeping in the same style as the previous slide, you'll notice that if there were no bias, I would hire them I would hire a Y candidate 1 over 1 plus alpha of the time, right? But with this bias, it's actually as if the size of my minority were not just alpha, but alpha times 1 over beta to the 1 plus delta. Okay, so it's as if I'm presented with a smaller minority. That's kind of the same effect approximately here. Okay, it turns out this is just a standard maximum likelihood estimation. You can get some solution for beta hat, and if you were counting, you can verify that this actually gives you beta hat equals 1 if you are actually, if you're 1 over 1 plus alpha of the time you are hiring Y candidates. Okay, so this kind of further strengthens our view that there is this kind of tight relationship between bias and viewing the minority as being even smaller than they actually are. Okay, so with that, conclude. So a lot of these proposals to deal with bias actually have impact on utility that hasn't really been considered as much as the push for diversity. And it turns out that some non-trivial analysis is actually necessary to assess their effects. There's a ton of ways that we would have liked to extend this model and still would like to, because I made a lot of simplifying assumptions, one of which was the fact that all my comparisons are actually deterministic. That's probably not the way that the world works, and maybe looking at some sort of a model where the minority suffers from a different level of noise than the majority would actually be kind of interesting. The other thing is the Rooney rule, the version that we've studied is to reserve exactly one slot. You could imagine reserving maybe L slots or some constant fraction of the slots. And there's this connection to optimal delegation that I wanted to mention. I don't have a lot of thoughts on it right now, but if anyone is interested, one of the reasons that the Rooney rule is effective in countering something like bias is because it actually doesn't offer your agents a lot of leeway to respond to it. in the sense that if you are a principal managing biased agents, and you need to get them to overcome their bias, I'll conclude right here. If you need to get them to overcome their bias, this is actually a way of getting them to do it where their dominant strategy is still to assess people as accurately as they can, as opposed to downweighting the minority for some perverse purpose. Okay, so with that, I'll say thank you and take any questions.